Hi everyone. Today we're going to do a practice problem related to single phase transformers in order to play with the concepts that we learned in class in terms of developing an equivalent circuit, calculating the voltage regulation or efficiency for a transformer. So let's assume I have been given a 20 kVA transformer with rated voltages 12 kV on the primary side and 600 volts on the secondary side. The parameters of this transformer are also given to me as R1 being equal to 30 ohms, X1, the leakage reactance of the primary side, as 45 ohms, R2 on the secondary low voltage side is 0.05 ohm, and X2, the leakage reactance of the secondary side, is 0.1 ohm. And then the core parameters R of C and X of M are provided as 50 kilo ohms and 40 kilo ohms. Pay attention to the significant difference between these values. So the core parameters are typically orders of magnitude larger than the winding parameters. The largest winding parameters that we have here are 30 and 45 compared to 50 and 40 kilo ohms. Now, the problem is asking you to do a few things. One is to derive the equivalent circuit of the transformer. And we're going to start with the T model in which the core parameters are in the middle of the circuit. It is also asking you to calculate what the voltage regulation and efficiency are, assuming the transformer is supplying the rated load at the rated voltage. And for the sake of this problem, let's say with a power factor of 0.85 lagging. That information, the load information, has to be provided to you. Without it, you're not going to be able to calculate voltage regulation or efficiency because the value of the primary side voltage, that depends on what you have on the secondary side. A lot of times the standard language is the transformer is supplying the rated load at rated voltage. And that basically is code for telling you that on the secondary side, rated load S2 equals 20 kVA, which is the rated power of the transformer, and rated voltage V2 magnitude is going to be 600 volts. But it is possible that the problem might say half a rated load at rated voltage, in which case you're providing 10 kVA at 600 volts. So be on the lookout for that particular language to tell you what you have on the secondary side. Let's start with the equivalent circuit. Because we are interested in the T model, the circuit is going to look like having the parameters of the primary side, R1 and JX1. And then we have R2 prime and JX2 prime. So these quantities have been referred to the primary side, which is usually the common way. It is possible for us to refer everything to the secondary side too, in which case you will have R1 prime and X1 prime and then R2 and X2. But oftentimes what we do is we refer everything to the primary side. At least this is what we're interested in this problem. And then because it's a T model, in the middle, you have your R of C and you have your J X of M. You have a load connected to the terminals, and let's say the voltage I have here is V2. Notice, however, V2 is the voltage on the secondary side. Because I'm referring everything to the primary side, I have to put that V2 prime there, and I'm going to place the tilde on top to remind myself that this is a phasor, not a scalar. The voltage on the primary side is just simply V1 tilde. There is no prime because it is the primary side. It hasn't been referred to any other side. We also have, let's say, the current on the primary side, again, because it's referred to the secondary sides, I'm sorry. Because it's referred to the primary side, there is an I2 prime and a tilde, and I have I1 tilde here. Now that's how the equivalent circuit will look like. What I have to do now is I have to find those parameters R2 prime and X2 prime. Remember that R2 prime, secondary referred to the primary, is A squared R2. And X2 prime is A squared X2. A is the turns ratio based on our definition is the voltage on the primary side to the voltage on the secondary side. So that's 12,000 divided by 600, which is 20. Hence, my R2 prime is going to be 20 to the power of 2, or 400, times 0.05. That's 20 ohms. And then for X2 prime, that's again 20 squared times 0.1, which is 40 ohms. Recall that this can be used as a sanity check when you refer impedance values from low voltage side to the high voltage side, they become larger. When you go the opposite direction from high voltage side to low voltage side, they become smaller. Because I'm going from the 600 volt side to the 12,000 volt side, they have to become larger, which is why we multiplied by A squared. That takes care of the first part of the problem. So this is our equivalent circuit, and we have all the parameters that we need. Next, we would like to find the voltage regulation and efficiency. However, in order to do that, I have to know what my voltage is on the secondary side and what the current is on the secondary side. For this, I always go back to the problem statement. What do I have? Rated load at rated voltage at power factor of 0.85 lagging. So what I can do is I can say my voltage on the secondary side is rated, which is 600 volts. And recall that usually the load side voltage is considered the reference. So we set the angle to be 0 degrees. However, what I am interested in is V2 prime, which is going to be A times V2. A is 20 times 600, which is 12,000, essentially the rated voltage on the primary side with angle of 0. What about I2? I2 can be found from the information provided. I2 essentially is S2. Notice there is no tilde on top of S. So this is the apparent power, not the complex power, divided by V2 with angle cosine inverse of power factor. But that angle could be positive or negative, and it depends on whether the power factor is leading or lagging. In this case, power factor is lagging. That means the current is lagging the voltage. Since the voltage has an angle of 0 degrees, the current would have to have a negative angle. So I place a minus sign here. If the problem would set 0.85 of leading, then you would have angle of plus cosine inverse of power factor. This is going to be the rated load, which is 20,000 volt amperes divided by 600 with angle of minus cosine inverse of 0.85, which is 31.78 degrees. That will be 33.33 with angle of negative 31.78 degrees in amperes. We are, however, interested in I2 prime because everything is referred to the high voltage side. So I2 prime, notice that for voltage, we multiply the secondary by A. For current, we divide the secondary by A. So that's 33.33 divided by 20, which will be 1.67 with angle negative 31.78 amps. Now I'm ready to solve this circuit. Let's go back and take a look at what we have. Essentially, what we have is two loops and a node. This is one loop, this is another loop, and this is the node. I would have to write a KVL for each of the loops and then a KCL for that node. And usually for these types of transformers, what we do is we start with the side for which we have the information. In this case, we have the information for the secondary side. So what I'm going to do is I'm going to write a KVL for the loop on the right. I have V2 prime. I know the values of R2 prime and X2 prime. I know I2 prime. By using that equation, what I can find is this voltage here, E tilde. Then I have to write the KCL in that node to find current of I1. And when I do have I1 and I already have calculated E, I'm going to be able to write a KVL in the loop on the left in order to find V1. I'll show you how we do this step by step. So let's focus first on the loop on the right. And let me perhaps clear this area a little to give myself a little bit more room. Let's do the KVL. So here I have E equals V2 prime tilde plus R2 prime plus J X2 prime times I2 prime. That would be 12,000 with angle 0 plus R2 prime is 20 plus J 40 times 1.67 with angle minus 31.78 degrees. This can be calculated as 12,064 volts with angle of 0.18 degrees. Next, I'm going to have to write the KCL in that node. KCL says I1, the current that enters the node, is I2, current that leaves the node, plus, let's call this I of E for excitation. And of course, I'm going to put the tilde on top as well. What is that excitation current? I already know the voltage E. By dividing the voltage E by the impedance of that branch consisting of RC and X of M, I can find I of E. What I can do is I can combine everything together and I say I1 tilde equals I2 prime tilde plus E tilde divided by R of C parallel with J X of M. And of course, you remember this can be calculated as RC times Jx of M divided by RC plus Jx of M. So what I have is I2 prime, which is 1.67 with angle negative 31.78 plus 12,064 with angle 0.18 divided by 50,000 parallel with J 40,000, 4 zeros. This is going to be 2.038 with angle minus 35.38 degrees. Now that I have I1, the last step would be to calculate V1. Again, let me clear this area a bit. So now my V1 in this loop, KVL will tell me that V1 tilde is going to be E, which I have already found, plus R1 plus JX1 times I1 tilde. So that's going to be 12,064 with angle 0.18 plus R1 and X1 are 30 and 45. So 30 plus J, 45 times I1, which I calculated as 2.038 with angle negative 35, 38. And that voltage V1 is derived as 12,167 volts with angle of 0.36 degrees. Now that I have this voltage, I should be able to calculate voltage regulation very easily. Voltage regulation basically tells me how much difference I have between the primary and the secondary voltage once the rated load is connected to the secondary side. So in this example, what I have for voltage regulation is the magnitude of voltage on the primary side, which is 12,167, minus the magnitude on the secondary side, but refer to the primary, which is 12,000, divided by 12,000. And that is going to be 0.0139, or you can multiply it by 100 and present it in percentage, 1.39%. That means you can expect the voltage to drop by 1.39% from the rated value of the primary to rated value of the secondary once you connect a rated load to the secondary side. Lastly, we have to find the efficiency. For efficiency, let's remind ourselves of all the losses for a transformer. A transformer, you provide input power, which in the case of a single phase transformer, that's simply going to be V1, I1, cosine of theta 1. Theta 1 is the angle difference between the voltage and the current on the primary side. The first component that is subtracted from that is the copper losses on the primary side, which is going to be R1 I1 squared. Notice that this is power losses. So we're dealing with the scalar value of I1. In other words, what the RMS value is. This is not I1 tilde. We also have the core losses, P of core, which is going to be RC times I of C squared, which is the portion of the current that is flowing through that resistor. But in order to do that, we're going to have to find that current. An easier way would be for us to say E, again, magnitude of E, not the phasor, E squared divided by R of C. And lastly, we have copper losses for the secondary side, which is going to be R2 I2 squared. And what we have is P out, which is V2 I2 cosine of theta 2. And of course, um, hopefully you remember from our discussion in class that V2 I2 equals V2 prime I2 prime, because in one of them, V2 is multiplied by A to become V2 prime. I2 is divided by A to become I2 prime. So the A's cancel out. You could have V2 I2 cosine of theta 2, or you can have V2 prime I2 prime cosine of theta 2. Both of them will give you the same thing. There are different ways that we can solve this efficiency. One thing is I can say efficiency is simply the output power divided by input power. So V2 I2 cosine of theta 2 divided by V1 I1 cosine of theta 1. This will be um, essentially V2 I2 is 20 kVA or 20,000 volt amperes times cosine of theta, which in this case is 0.85, or rather theta 2. And then V1 is, as we found it, 12,167 times I1, which is 2.035 times the cosine of the difference between the two. The angle of voltage is 0.36. The angle of current is minus 35.39. If you add them together, you're basically going to have cosine of 35, let's say 0.7. You find this ratio and you will get an efficiency of 0.846 or multiply by 100, and that will be 84.6%. Another way to do this would be to look at it not as the output power. So this is P out to P in. Rather, we can say this is P out divided by, instead of P in, I can say P out plus P of losses. They will both give you the same thing, of course, but sometimes people prefer to do it the second way. And let's do the second way as well. So P out obviously is 20,000 times 0.85 and 20,000 times 0.85 plus these losses, R1 I1 squared. So that will be 30 times 2.035 squared plus P of C, core losses, would be E squared, which is 12,064 squared divided by 50,000 plus R2 I2 squared, or similar to before, this is the same as R2 prime I2 prime squared. So both of them will give you the same thing. Let's do R2 and I2 squared. So or rather R2 prime I2 prime squared. So that will be plus 20 times 1.67 squared. And again, if you do the same analysis, you're going to get the same results of 0.846. Now, before we stop for today, I want to go back and revisit the problem of solving the circuit if instead of this equivalent circuit of T model, I would be using the simplified model in which the core parameters can be shifted all the way to the beginning of the circuit. So let me go ahead and erase these equations here. I want to show you guys that how much easier things become when I can make that assumption. So let's remove some of these things that we don't need. And what's going to happen is I can assume that I can work with the simpler model in which I have my R of C and X of M, or JX of M rather. At the beginning of the circuit, I have my V1 tilde. I have my I1 tilde. And then I can basically get rid of this component here. Let me perhaps use this selection tool and erase this part. I just hit something and made it very big. Sorry about that. All right. So this is my line now, and I do not need this loop. So if I can ignore, or not necessarily ignore, but move that shunt branch to the beginning of the circuit, this is the equivalent circuit that I will have. The analysis of the shunt branch is really easy. You have the voltage across it, you can find the current through it. So what we really have to do is to solve 1 kVL for that one loop that I have. Notice that instead of solving 2 kVLs and 1 kCL, all I need to do is just 1 kVL. And what I have is my V1 tilde is my V2 prime tilde plus my R equivalent, which is R1 plus R2 prime plus JX equivalent, which is X1 plus X2 prime times I2 prime. This will be based on the values that we had. It's going to be 12,000 with angle of 0 plus R1 is 30, R2 prime is 20, so 50 plus J. X1 is 45 and X2 prime is 40, so 85 times I2 prime, which I found it to be 1.67 with angle of minus 31.78 degrees. This can be calculated as 12,145 with angle of 0.36 degrees in volts. And if you do voltage regulation, you will have the magnitude 12,145 minus the rated voltage on the secondary side, refer to the primary, of course, 12,000 divided by 12,000. This will be 0.012 or multiplied by 100 and you can get 1.2%. As you can see, there are a number of equations that you have to write to solve these equivalent circuits of transformers, but because all transformers are modeled in either of the two ways that I discussed today, you basically have to use either of those two sets of equations. So it doesn't really matter what values or parameters I give you, you still have to either write and solve 2 KVLs and 1 KCL for the T model or a single KVL for the simplified model. So hopefully this gives you a better kind of an insight into how you would solve a transformer, and you feel more comfortable with these concepts that we talked about in class.